Hi, everybody. This one is going to be a real seat of the pants experience, DRAT experience, more so
What
than usual.
when isn't it?
No, that's fair. That is fair. Okay, I'm going to share my screen. All right, y'all see this? Good. Here we are. Who here wants to take a stab at what assembly language is?
Something low level.
Something low level. That's true, although it doesn't narrow it down very much.
Is it like
Man.
CPU instructions?
Yeah, it's getting there. So yeah, assembly language is a very low level programming language. It is not CPU instructions, but it maps nearly one-to-one with CPU instructions. So CPU instructions are what you see inside of an executable program. So I just ran a make command that's going to build this C program into an executable. This executable does a very simple thing. It just prints out hello world. But if you look at this thing, this executable file that was created, opened with text editor, you're going to see somewhere in here, there's a lot of zeros. I think it's mostly, there's a lot of padding. But there are going to be machine instructions in here. It might be starting around here. And these machine instructions are, actual bytes that a CPU that get loaded into a CPU's, into a CPU and executed. Assembly looks a little bit higher level than that. So, I mean, there was a time where, you might actually find yourself in a hex editor modifying byte values to write your computer program. Sadly, those days are long behind us. I think what was sort of invented after that, to eliminate some of the tedium of actually writing machine instructions byte by byte, was assembly language. So this is a variation, this is a variant of assembly language. So this is ARM architecture assembly language, which is different from Intel or x86 assembly language. There's other assembly languages as well. But they all look kind of similar. There's a lot of similarities. And the things that you can do in an assembly language, well, you can do anything in assembly if you're patient enough, but the things that you can easily do in assembly language are like a handful of very low level operations. So I'm going to compile this. I compiled this C program into an executable. This assembly language program, I'm gonna also, how do I compile it actually? Oh yeah, okay, I made this make run thing. So I can actually hello world hello world. Oh, I didn't actually make a command for building it from assembly. So let's remove hello world. Shoot, what is the command? Now I completely forget. Mac OS compile assembly. What is the thing? Mac OS M1 compile assembly. There we go. AS. Oh yeah, here we go. This is the guy. Oh, okay. It actually is maybe doing the right thing. Is it doing the right thing? Oh yeah, okay. All right. So this is actually an assembly language program compiled from this assembly file. And the way that or the things that you can do in assembly language easily are very basic primitives. So you can move bytes or integers around from memory location to memory location, or from memory location to registers, which are basically sort of memory on board the CPU. So it's distinct from system memory. So there's like a very small number of what are called registers, and registers can hold bytes or integers or floating point characters, or floating point numbers, and they can do within those registers, they can do simple operations. So you can perform additions or subtractions or multiplications within on values within those registers. And the way that you do that, you can see here I'm moving into the register X0 the value 1, so the literal integer value 1, which in this case is standard out. I'm going to move I'm going to point X1 at this value hello world, which is basically just a string of memory within the executable. So this is sort of how you declare constants within the actual executable. And if you look at the executable, you can see that down near the bottom, there's this literal string, hello world. Or wait, sorry, that's not the right hello world, is it? It is with an exclamation. Can I not search? Oh my God, why is this happening to me? Somewhere in here, there is the string hello world. It is at the bottom, I think. There it is. Okay. So what this has done is basically this literal string, these characters, hello world, new line, have been stored inside the actual executable. And within the assembly language, I can reference this as a symbol, as a name or a variable. Well, not a variable, it's like more like a constant. And so I can reference that memory and perform operations on it. I'm going to basically put a few values into these registers X0, X1, X2, and X16. And then I'm going to basically make trigger an interrupt, or like trigger a system call. In this case, system call hexadecimal 80, which is a write operation. So I've put into X0 the output file, or the file descriptor, which in this case is, I'm using standard out, which is always file descriptor 1. And I have put in X1 the address of our hello world string. I've put in the length of the hello world string into X2, and specified system call number 4, and triggered, basically relinquished control to the kernel to execute some operation. In this case, like a file write. So when you are, performing operations like file writes in, whatever language, underneath it all, there's something like this happening. There's some kind of trigger some kind of trigger that's resulting in a file write system call. Then I'm going to do sort of this, basically shut down the program. I'm going to basically make a system call 1, which is to terminate the program. But before that, I'm going to put into X0, register X0, the return code of this for the program. So like when you exit, in C, this would be like a return 0 from the main program. So basically I'm doing 2 system calls here. One to print the string hello world, and then one to terminate the program. So this is really sort of demonstrating like how interaction with the operating system happens. But there's lots of other things, we could be doing here. So for example, we could move into EAX. Oh wait, is this gonna work? We're gonna try some things here. So I'm gonna use the register EAX. Which is a sort of dummy register, like just for scratch values. And then I'm going to add EAX, and I'm going to add to it the number, say 9, and then I'm going to move into X2 the value of EAX instead of the literal 13. So this should do the same thing. Let's see. No, it doesn't like me adding a literal value of 9. So we're going to move into EBX, the value 9, and then we're going to add EBX to EAX. Nope. Oh, maybe I want move into the value of EAX, the value of EAX plus EBX. Sweet. This is great. How do you add shit in I was sure this was about right, but yeah, I think you can add. No, doesn't like it. Okay. In any case, great tutorial, Dylan. But the sort of point I'm getting at here is like there's very sort of low level operations that you can do, you know, with these different assembly operations. So like moving things to and from registers and to and from memory locations are a couple of things you can do. You can also, you know, do operation like simple arithmetic operations like add, subtract, multiply, and then the other sort of really important one is around branching. So instead of you know, there's no such thing as sort of like the higher order you know, function calls and or loops or anything like that. All of those things are like more complex operations that you can do in higher level languages are actually composed of smaller operations. So, you know, if we were going to write a loop, we might do something. This is not going to work because my assembly, do not remember all of the details of like writing this, but if you were going to do a loop, you might do something like move to register EAX the value 0, and then you're going to compare EAX to whatever, you know, the upper limit of the loop is. So for example, let's say 10, and then so we're going to loop from 0 to 10. Then we're going to do branch not equal. So if EAX is not yet equal to 10, then we're going to branch not equal, or sorry, branch if equal to like, you know, the end of the loop. And otherwise we're going to do stuff in loop, and then we're going to add you know, 1 to the loop counter in EAX. So this is what a loop might look like in assembly if you know, you were to actually write it out. Similar to if you're making a function call, and I should put end loop here. So I should also you know, say that like a function call is basically just a branch or a it's sort of like a go-to, right? So there are with function calls, there's also the consideration of arguments. So for function arguments, generally speaking, function arguments will use or will be passed on what's called the stack, which is like a data structure in memory in all programs that basically captures a few things about function calls. So things like the address that you should return to when you're finished a function call, as well as like the memory, potentially the memory locations of or even the values of the arguments being passed to the function. So when you're making a function call, you're going to do something like, you know, push the value of, you know, push the, I don't know, push the value 10, push the string memory location of our string hello world. And then we're going to, I think, in fact, there might be a call, maybe not. So basically there's going to be a branch to, you know, our function. And actually we're going to push the return where we're going to return to when the function is complete. So, you know, we might have a label like that, and we're gonna push the return address that we're going to jump back to when the function is done. So we pushed our arguments, we pushed the return address, and now we're going to branch to function. And then function might look something like this, where it's going to pop into, I don't know, EAX is going to pop into EBX, those values that were pushed onto the stack. And then it's going to do something with arguments. It may, it will do something with the return value. So it might actually put it into a register or something like that. So like, you know, move result, move the result into EAX. And then whatever, maybe this is our result. And then it's going to pop probably the return address into a register and branch back to the location that was put in the stack to begin with. So like you can kind of see like this is very tedious, and like you can sort of start to understand like why higher level languages like C were invented. So like all of this stuff where we're, you know, pushing arguments onto the stack, we are pushing the return address where we should go back after the function call is complete. And then, you know, dealing with return values, all of those things are completely abstracted in a language like C. So we can actually look at this in a little bit more detail. So like, let's say we have a function foo, and we're going to call foo, and we want to compile this. Did I make a way to compile this? Is this going to work? GCC hello world.c. Oh wait. How do I Mac OS M1, or actually Mac OS compile C to assembly? I did this, but now I forget the command line. Well, I can't remember how this to do this because I didn't put it in my make file. But in any event, there's you know, there's a way. It's a pretty simple command line with GCC to actually output assembly language from a C file, and you can kind of see how, like, what kind of the output of that is. But you know, what actually comes out is like quite a complicated program, even for something as simple as this. This is sort of the main stuff that I wanted to talk about. Any questions about assembly language, or like what, you know, how this stuff works?
The second variable, from what I understand, is either a register or memory allocation. Like the XO, X1, EAX, EBX, all that stuff.
Mm-hmm.
Is that a correct interpretation? And what is there any difference between a register and memory allocation, or are they kind of the same?
No, they're not the same. So a register, basically onboard a CPU, or well, onboard a core. So every core within your CPU has a set of registers. And those registers, there's a limited number of them. So like in a modern CPU, there might be, I don't know, 30 or 60 like different registers. Probably, actually, maybe even less. I'm not actually exactly sure how many there are, but so there's a very small number of them. Each of them can store as many bits as typically each of them can store as many bits as the CPU has bits. So if it's a 64-bit machine, the registers are 64 bits wide. There are certain operations that the CPU or the core can do only on values within the register. So it may or may not be able to, it depends on the CPU, but generally speaking, like adds and multiplies and things like that cannot operate directly on memory, like system memory, like your RAM. It can only operate on things in your register, or at least one of the operands needs to be stored in a register. There's there's a very small number, you know, it's a total of like a small number of kilobytes of sort of this like very you know, important kind of memory on board the CPU core. System memory is like your RAM, right? Like that's like, you have whatever, 16 gigabytes of RAM. You can do certain things on system memory directly from a core, but for the most part, what you do is like move stuff from system memory into a register and operate on it, and then move it back to system memory. There are, now that's a generalization. There's lots of like lots of like basically, you know, architecture specific things that like you can do to memory, you know, direct memory access from the CPU. But in general, like the registers are where like most of the operations happen.
Thanks.
Other questions?
Is assembly like the go-to for low-level languages? I'm assuming like C++, is that considered like on the same level as assembly?
No, I mean, it's kind of a blurry line, but like basically you can think of it like machine instructions are at the very bottom. That's just like the bytes that are in your executable file. Then assembly language is a slightly higher level abstraction on top of that. And then there's like sort of system programming languages that tend to compile into raw executables, like C, and C++, even Go, maybe it could be considered that. And then there's like interpreted languages like JavaScript, Python, languages like that, where the operations themselves are abstracted and happening in a sort of virtual CPU. So for example, Python is like the format of compiled Python is actually bytecode, which is which it interprets, and then it has like a sort of in software. You can think of it as like a processor that actually processes things at that level. So that's sort of like the breakdown, like a rough breakdown of the levels of languages.
Thanks.
Let me see how to phrase this question. How do you handle if you are passing too much data to registers and memory? Because I assume that you have to be careful with that, right? So you are being very low level and you have limits in how much information can pass to what. Does the compiler help you with that? Like what happens if you put a very big string into a single register, for example? Like what does the compiler does in that situation? Does it throws an error, or it runs and things just is broken?
So if you try to sort of put too much data into a register.
Yeah, exactly.
Yeah, so what's actually happening here is not, so it's not the case that this whole string, like this hello world string that we defined down here, all of this is being loaded into the register. It's actually the address of this string. So what actually is happening is the string is not being moved, onto the CPU. It's actually just the address, and the address is always a 64-bit in a 64-bit architecture is always a 64-bit integer location within memory. And so there's no that's not a concern. And in general, there's not really I mean, it's sort of weird because we tend to not really think about we tend to not really think about addresses as different from values, or references as different from values in a lot of languages. But a string is always a reference. So you're never really dealing with you're never really moving around the contents of a string in the way that you're kind of describing. You're actually just moving around a reference to that string. Values are different. So when you have a 16 or a 32-bit or a 64-bit integer or floating point value, you do move those, or you copy those, you potentially copy those from memory into a register to operate on. But does that kind of answer your question?
Yeah, it still brings the next question though about how are strings, there you will just say, give me this string, and gave you one address to reference for, but that string might not serve in a single address in memory. So how does that work for you to know how that reference points to a bigger string? Because I assume there are limits there, right? I'm sure if that question doesn't make sense, feel free to ignore it. I'm very dumb in low level programming.
Yeah, so I mean, there are certainly limits, right? Like, but generally, I guess generally speaking, unless like you're talking about a string that is bigger than the 64-bit address space, there's not really a worry about like the size of a string as it relates to like individual CPU operations. Like if you need to operate on that string, typically what you're going to be doing is like moving bits of it into, you know, a register operating on that. So for example, like if you're comparing two strings, right? Like the way that that would actually work is you have two strings in memory, and you move the first two. I mean, probably they do it, you know, say 64 bits at a time. So like 8 characters in an 8-bit encoding. Like move 8 characters into one register from the first string, move 8 characters into another register from the second string. Compare those. If they're different, then you know that the two strings are different. And if they're the same, then you sort of continue processing the string until you do encounter a difference. So like, you know, that sort of string comparison, which is really comparing like many bytes, many pairs of bytes, is decomposed into like a loop that is comparing just, you know, 1 or 2 or 4 or 8 bytes at a time.
Yeah, that makes sense.
It's a good question.
At what point, like for I guess most of us working in obviously higher level languages, is I guess understanding any of this help us in, like, is there any specific types of examples of projects or ideas where I'd have to, hypothetically speaking, like understand more of this? So for example, over the last couple of weeks, you've mentioned bits and bytes, and having some understanding with that. My question makes sense. I know like where I'm.
Yeah. So I mean, look, I mean, you're never going to need to do assembly language programming. Like most programmers never actually write assembly language code anymore, right? The thing to be aware of is sort of like more fundamentally how shit works on a computer, right? Like, you know, the it is you know, more sort of relevant to understand like ultimately what is happening when your code executes, and like the basic concepts actually do kind of bubble up to higher level languages, right? Like that's why, for example, in you know, why we have the basic data types that we have in higher level languages. Those you know, strings and like strings and numbers, like integer and floating point numbers, and arrays of those things are basically all that we have at the base, at the bottom of everything, right? So like sort of understanding like what your, like how your language treats these different kinds of primitive data types is kind of important. So for example, in like the Go programming language, there's like fixed width numbers. So there's like 8-bit or 32-bit or 64-bit integers, and 32-bit and 64-bit floating point numbers that actually map to, you know, sort of memory locations and are operated on in a very primitive way, you know, on the CPU. So like in the Go programming language, you're pretty close to you know, what actually happens on the CPU for some kinds of things. In JavaScript, you know, understanding how numbers work in JavaScript is kind of important at some, you know, or in Python, say, right? Like numbers, there's a reason why this actually, I think, has changed in Python. I think now numbers can or integers like become big integers at a certain point, but in Python, like when you're operating on small integer numbers, you're actually like working with say 64-bit values that ultimately, when you add them, are being added on together on a CPU. Now there's more sort of abstraction on top of that, because when you add two 64-bit numbers and it overflows what can be stored in 64 bits, Python actually grows that, I think in Python 3 anyway, like grows that to a variable with integer that can grow, you know, as big as your memory. But like, you know, you're sort of like nonetheless, like you're sort of operating on things in a pretty primitive way in most languages when you sort of get down to it. So I think it's useful to sort of have a model for how this works. I don't think it's important to be able to like write programs in assembly, but I think it's important to understand like you know, what ultimately is going on a computer, so that you can because that bubbles up to implications for like how your, you know, higher level programming languages actually work.
Okay, that makes sense. I guess in general, or not in general, but like, is there any common, I guess, architectural decisions that you've learned from having a basic understanding of a low level language like this? For example, using strings as opposed to numbers potentially, in like a database or whatever have you. I don't know, but like, is there any like common rules or architectural decisions that you
yeah, I mean, I think like when it, you know, when you do need to think about like things like storage or efficiently storing things, or you're dealing with like large scale sort of considerations, like understanding that like, you know, an array of 64-bit integers is going to be fundamentally more sort of I guess is going to be like, say, more efficient than storing you know, string values, because there's a level of indirection there with strings that may not be sort of present with integers. So, you know, or in a database, like if you're storing, thinking about like, okay, what's the minimum, you know, amount of data that we can store for a particular column to like avoid a bunch of, you know, wasted space, wasted storage. It especially comes up when you're like dealing with like really high volume stuff, right? Like not the typical kind of like entities that we deal with, where like, you know, maybe we're dealing with like thousands of records or tens of thousands of records, but like when you store something, say, for every single action that a user does, you know, thinking about how data actually is laid out, sort of becomes relevant.
Was there any like example of that at yours and Matt's time at like YouTube or Slack, or where you had to make like decisions based on, because obviously that's more at scale. So I'm assuming potentially decisions could arise like that.
Yeah, I mean, I think at YouTube there was definitely some crazy shit that we had to do with the Python interpreter, like at a very low level, sort of changing the way that certain things are represented. So, for example, the way that the Python reference counting works, so for every Python object, there is a reference count associated with it, and every time you reference it in a variable, that reference count is increased, and then every time a variable goes out of scope, that reference count is decremented. And so what happens in in that particular architecture, there's a lot of small objects, and so like, you know, we had to I won't get into too many of the details, but like basically there was like you know, a lot of small objects in memory that are, and it's relevant that like the values of those in those small objects were changing. That is, they weren't sort of immutable values. So there was some like weird shit that we had to do to like, you know, make the memory usage a lot more efficient for those kinds of small objects. Like another example, or like I guess I'm saying a more abstract example, is like something called memory pooling, where like instead of allocating memory from the heap, which is a section of memory that's reserved for your application when it starts up, when you allocate on the heap, what can happen is that as you allocate and free that memory, it can become fragmented, and when you have many small objects being allocated in that heap, the fragmentation basically reduces it makes memory allocations less efficient over time, and it potentially reduces the amount of memory, sort of usable memory, that you actually have. And so, you know, memory allocation, so a pool allocator will basically dedicate some section of memory to allocations of a particular size. So say like 8 bytes, if I'm allocating lots of 8-byte objects in my program, I might dedicate a section of memory to 8-byte allocations, so that I can pack them into that space more, and they're not going to fragment the broader heap. So like these are things that happen in your language runtimes. So like, you know, Python has, for example, like, you know, a lot of like specialized allocation logic for like, you know, these kinds of considerations. So, you know, generally speaking, unless you're like working on a language, like it's not necessarily something you need to think about, but like it's sort of useful to know and understand and be able to like have a model in your head about you know, what is ultimately going on, you know, with the variables with the data you're allocating in your program.
Yeah, makes sense. Thank you.
I think a practical example in that line too might be, correct me if I'm wrong, there was a time that YouTube got a problem with too big of an int, that it like you need to update the type of that field because there was a limiting that you reach the maximum in that database field. So if you have a feeling of how types work internally and you need to update your database type, you need to estimate how much space you start to waste in those older records too. Like how much extra space I need for the records that already exist now that I update this integer to be larger for future records as well. And what will be this cost in my architecture. If you don't know how types work internally and you can make that estimation correct, you might underestimate or overestimate your extra costs and your infrastructure overall performance there. So I think like understanding this might be helpful in those cases as well, where you reach limits and you just need to understand better the impact of changing those limits. And
Yeah, that's a great example. Like another sort of example is like how strings are stored in a database. Like generally speaking, there's a couple of ways that strings are stored in memory. Like one is that there is a zero, they're null terminated. So there's a byte 0 at the end of the string. Another format is to prefix a string with a value like, say a 64-bit value that prefixes the length of the string. So like when you're thinking about how, so in databases, many databases have like different string representations, or they have fixed, like they support fixed length strings. So like thinking about like, does my field, if I allocate a fixed length, if I know that my string will never exceed 16 bytes, maybe I can use a fixed length string that will only require 16 bytes for every single string, versus having a prefix, like an 8-byte prefix, length prefix string, which will always sort of waste those 8 bytes. And then in addition, putting additional, like the rest of the string at the end of that, like just like thinking about like how the data is actually stored is important to like, estimations and being able to like size your database correctly and things like that. All right, that went longer than I thought. Any other parting thoughts?
So assembly is good or bad?
Wow. Boil it down to good or bad. It's a useful, I think it's a useful exercise to like think about like the basically like how these things work. The thing is like how assembly language or how your CPU works basically, or how your computer works, is also how languages are implemented. Like, and that starts to, again, kind of like bubble up into like considerations about like how you structure your code and things. So knowing a little bit about assembly language and how CPUs work helps you understand particularly how interpreted languages work. Is generally kind of a useful thing. At the end of the day, all the data structures and all the like, complicated things that like functions and things that you call every day, boil down to these like super basic operations and moving stuff in and out of the CPU. And it's I think it's useful to have a little perspective on like what's actually going on there.
Very cool. Thanks a lot, Dylan.
Thank you all.
Good, Dylan.
Thank you.
Thanks, Dylan.